Hello. Hi, everyone. Hope everyone's having a good day. Um, I know I certainly am. I didn't get up too long ago, but it's been a nice, relatively chill morning. I got a little bit of exciting news. This stream, so I decided I wanted to break up the, just doing hardware design all day thing, and have something else to do as sort of a break during the hardware design. And so we'll get there. I'll do my first break in like an hour, and then you'll find out what it is. But it's exciting. Um, all right. But yeah, if you weren't here last time, we figured out that we can use a USB-C connector and have just a full speed or I don't know if we'll need full speed or high speed. We can do like a full speed or high speed, just standard USB-A connection over a USB-C connector. And that doesn't really give us a lot of advantages. Like, we can't necessarily trust, we can't rely on having a higher current amount, because if someone plugs in our device with like an A to C cable, then we can only still draw the USB-A 100 milliamps without negotiation, 500 milliamps with negotiation. But it does offer the advantage of being able to use the USB-C connector, which I feel like it seems like more human devices are being built with those connectors rather than the older USB connectors. So switching to that sort of helps us future-proof a little bit. That being said, we laid out quite a bit yesterday. We laid out the connector, the control logic block that will basically let us figure out which way the USB-C connector is plugged in and how much current we can get out of it. We laid out our power management IC, what is the one that takes the 5 volts that comes through the USB connection and basically turns it into 3.3 volts, because that's what we need for our microcontroller. And then we did some basic first pass schematic layout on the microcontroller itself. Now, thankfully, this project shouldn't require a whole lot more layout. The thing is, we don't have anything super complex going on. If we were going with the LCD situation, where every button has an LCD on it, then it would be a very different matter, because we would have to deal with a lot of different connections for all the LCD pins and figuring out how to get those and get them the current they need and get the connections to the microcontroller. But as is, it's not really so much of an issue, because all we need to do is connect buttons and LEDs. Oh, hold on. I have to mute my Windows XP virtual machine. Spoilers for what the secret break topic is. It does involve the Windows XP virtual machine. There we go. I just paused the virtualization there. And so, yeah, I think that today, if we go long enough and if we get stuff done fast enough, we might be able to get just the whole PCB laid out today. I'm not going to make any promises. Not going to make any promises. I certainly can't tell you for certain that we're going to do that. But, it's possible. Okay. With all of that out of the way, just jump right into it. So, put myself back in the corner here. Yeah, I'm going to get our background music going. I guess it's already going. I just haven't unmuted it. And as always, let me know if this is too loud or it's hard to hear me over it. It's looking like with the ducking I have on it now, it should be okay. But also, I thought the same thing about the Minecraft stream last Tuesday, and it was not okay. So please do let me know. I did a little test recording and it seemed fine. But again, better safe than sorry. So, okay, let's jump right back into it. So this is our schematic as it currently stands. This is the USB-C connector itself. And as you can see, we're not using any of these pins right here. These pins are just, these pins are for, like, higher speed communication. They're for, like, USB 3.0 and 3.1 super speed. I don't think I need to use these pins, these SBU pins, but I didn't mark them specifically as not connected because I'm not 100% sure. And then, yeah, these bus pins are connected to our V bus. These ground pins are connected to our grounds. The control logic block, which is the part that lets us determine whether our connector is plugged in the right way, or like whether it's plugged in right side up or upside down, basically. And which also lets us determine how much current we can get from it. Hold on one moment. Just making sure we can get some decent quiet so that my communicator doesn't buzz us during the stream. This is our control logic. These resistors are specified, like in the specification, they have to be 5.1 kiloohms, they have to be plus or minus 10% or better. That being like the allowed error in this number. It's like 10% means that this resistor could be 5.2, but if it's 5.21, then it wouldn't, like we wouldn't get a resistor that's 5.21 because we're getting specifically a plus or minus 10% resistor. And again, that's just to make sure, because if the resistance is off, then that means the voltage we measure is going to be off. And with the way the thresholds are set, this is how accurate it has to be for there not to be a significant chance of us accidentally making the wrong decision by reading this line. Because once again, the voltage that comes through on this line, which is dependent on this resistor and also a resistor on the side of the computer on the other end of the USB cable, tells us how much current we can draw. And so if we get the wrong number from this, then we might accidentally draw too much current because it looks like it's saying we can draw 3 amps, but actually we can only draw 100 milliamps. Yeah, that's why they specify 10% accuracy on the on these resistors here. Okay, and then this is our USB multiplexer again. Because the cable can be connected in one of two ways, we only need one D plus and one D minus, but there are two on the cable. Only one of them will be connected through to the computer, the other we need to not use, basically. And while we could just tie them together, because of some signal properties, we get better performance if we use an actual IC to basically act as a electronically controlled switch to connect us to either the A6 A7 pair or the B6 B7 pair. That's what's going on here. These CC pins are connected to ADC inputs on our microcontroller so we can read the voltage. This output enable output is just a pin on our microcontroller that we can control to set which set of USB pins this is connected to. And so basically I'm moving that determination. So we don't have to use our microcontroller for this. We can use some like comparator ICs, like you could set up an op amp to do this automatically. But because we're just prototyping for the first time and I don't have a lot of experience with this, basically, if it's a hardware component, then it's very hard to, like, change it, you know? if I did it wrong and I have to go back later and change it, then that's going to be difficult. Because, you know, it's hardware on the PCB. But if they're both just connected to the microcontroller, then that makes it more likely that if I have a problem, I can solve it by just tweaking some software, which is much, much easier. That's the USB port. You'll notice we have these signal buses. All these blue wires are actually multiple wires on the same line. So you can see this USB bus, which is what these blue wires are called, has all of these pins in it, and you can break them out at the other end. This USB power bus has these two lines coming into it, which are the USB V-bus and ground. Importantly, this V-bus is at 5 volts, but we want to run our microcontroller at 3.3 volts. So, like, our main power supply will be 3.3 volts, but we need to get that from 5 volts. So we go to this power management section, where we have a voltage regulator, which is a little device that is designed to take in 5 volts on this end and put out 3.3 volts on this end. And to do that in, like, a stable way, you know. There are, like, simpler ways to do it. Like, you could just do it with, like, a voltage divider, you know, 2 resistors. But that method ends up being very sensitive to the amount of current you're drawing through it. So, I think it's something that is less sensitive to that. We use this dedicated IC, which is designed to be very not sensitive to current as long as you're not overdrawing its current rating. USB power supply comes in here. And we get 3.3 volts out and our ground connection. Other thing that we implemented here, the USB connection comes into our microcontroller. Just a reminder, so this chip has an inbuilt USB physical layer that lets us communicate over USB without having to worry about the nitty-gritty details of, like, everything involved in negotiation and setting up the, like, physical layer and doing those differential signals. The microcontroller takes care of that for us. But to do that, it does need the V-bus, that 5 volts, coming in on this pin. So we give it that, and then we give it... We give it the USB D plus and D minus. Communicate out. Both of those configuration logic pins come in on this pin and this pin, and I chose those pins because if you look at the technical reference manual for this device, let me find that. I should remember to save this next time. I'll have to go grab it from the instructions. So the analog to digital converters, actually, I believe those are actually in the data sheet rather than the technical reference manual, so let me grab that as well. Yeah, so in A6 here is unfortunately, I have to kind of dig around to figure out which pin it is. There it is. Is input 3 to ADC 1 and 2, and in C4. Hold on, spoilers. and C4 is connected to ADCs 1 and 2, input 4. So we're going to use ADC 1 to monitor those two pins, and that will tell us what orientation the USB connector is plugged in, and how much current we can get out from it. I noticed while reading the spec, I believe this was on stream last time, we do need to continuously monitor those pins in case, like, because the device on the other end is allowed to change it, like, midway through, you know? So unfortunately, that's not just something we have to monitor on startup, that's something we have to keep an eye on. And the output enable, we're just connecting this here to use it as a general I/O pin. So this is just a pin that we can turn on and off, according to our program, and, like, you know, set the USB connection appropriately based on what we read in from these two control logic pins. And we will get more into that once, like, we get to the point where we have a PCB and we're programming it. Which, I don't know how long it's going to take them to make, but it'll probably be a couple of weeks before we get it back. So just be aware of that. I don't know what we're going to do in the meantime. It probably will take more than a week. So I don't know, maybe I'll just put something else in this slot next week, assuming we get this PCB layout finished today. Yeah, first things first, we have to get this set up. I wanted to see if there's, like, a sample, like, example implementation here. On the microcontroller's datasheet, it will basically tell you, I know, what you want to do on all of these microcontroller pins. Microcontrollers will give you, like, a here's an example application, here's how we recommend you connect the different power supplies and, like, the ADC inputs and things like that to ensure maximum performance. Okay. That is probably good information. See, I don't know if this thing has an internal oscillator. Let me check real quick. If not, we will have to worry about getting an external crystal. Because these microcontrollers are dependent on a clock signal, which is just a really fast signal that goes up and down. So it goes up and down real fast in a square wave, and that's kind of the foundation of human digital logic, you know? Because that signal lets you synchronize things and get logic to where it needs to be, and like store data and do everything like on a sort of steady march so that everything happens at the same time. A lot of microcontrollers will have an oscillator just inside of them, usually like a couple inside of them, but you can also attach your own external oscillator, which allows you to get more precise conditions. It allows you to sort of set some extra stuff. If this microcontroller has an internal oscillator, I'd say probably we're just going to use that, assuming it's at a reasonable frequency that we can make good use of. Otherwise, I'll need to get an external crystal, and we put that right on the PCB and have some little supporting logic around it, and then hook that into microcontroller pins, and we can just tell it, hey, this is your clock signal, go off with this. What I was looking for. I'm going to need this information for how to connect up the power supply. Make sure that I have... Okay, yes. The device embeds 4 internal oscillators, 2 oscillators with external crystals, 2 internal oscillators with fast startup time, and 3 phase-locked loops. I think I've already explained what a phase-locked loop is. That's what PLL stands for. Basically, it takes a slow clock signal and generates a faster, but usually like less accurate clock signal. So that's generally something that happens a lot of the time. Instead of having to get an oscillator, like a crystal that can actually oscillate reliably at like 500 megahertz, they have one that oscillates at like 64 megahertz. And then they stick that through a phase-locked loop to turn that into 500 megahertz. Yeah, that should be fine. I don't need to worry about putting an external oscillator on this thing. HSI clock, we can then select the clock configuration. So basically it has to start on something in order for our logic to run, but once our program like starts up on this, we can like wake up and say, okay, we want to use this 32 kilohertz clock, which we probably don't want to. That's very slow. But you know, just as an example. Alright, let's take a look at this power supply manager. Description. 2 to 3.6 volts. Right externally, 3 VDD pins. This microcontroller does support like a battery backup. Basically, it has an entirely separate like domain that is on when the battery backup's enabled. So you can sort of prioritize things and say that when we're in like the battery backup state, we don't need to measure this or this or this. We only have these very core peripherals enabled, but we don't need to do that. Our device is going to be bus powered anyway because it's a USB device and we need to send data. Like, it's not going to be particularly useful. Like, if we don't have a If we don't have a USB connection, our device isn't particularly useful, so we can just let it turn off when the bus power's gone. That's so true. I've heard that background music should be peaking in the green. Turn that down a little bit so that it actually peaks there. That looks better. So that's what this power supply is, basically. So we can have a little, like, backup cell. Which, like, I don't know, maybe something we want to think about later as, like... Because it's possible, right, that we could have a situation where we are writing files to our, like, internal SD card, and then someone pulls the plug while we're doing that. And the safest thing to do there would be to have a battery backup that powers just, like... It powers enough so that we can, like, close out the file system safely so that we don't risk corrupting our file system when someone plugs it back in. Now, granted, the user shouldn't be doing that anyway. So if someone unplugs our device, then, like, it's their fault, not my fault. That is entirely humans' fault. Okay, nice to meet you too. During power up and power down phases, the following power sequence requirements must be respected. VDD 33 USB must remain below VDD plus 300 millivolts. They don't specifically mention the, like, normal USB voltage inputs. I guess I'll have to, like, keep that in mind. Because, you know, I don't want, like, we are, as things are right now, the USB power supply will probably come on before the 3.3 volt supply. Like, the 5 volt USB power supply. I think because we're not using their, like, internal USB voltage regulator, it should be fine. I'm not 100% sure on that. Regulator output adjusted according to application needs through 6 power supply levels. So yeah, this is what we were seeing on the power draw, like the current information and electrical characteristics. So we have a sort of lower power mode, there's like a medium mode, and then there's like a high performance mode that will draw more current, but it can run faster and do more. And then there's a, like, much higher power consumption mode. We're probably just gonna stick down here in the low power mode. I know definitely we're gonna want to start, we're definitely gonna want to start in the low power mode. Because, if you'll recall from last time when we were reading the USB specification, we can only draw 100 milliamps. in the earliest stages of powering up. While we are negotiating the USB connection with the host, we can ask to raise that up to 500 milliamps, which is sort of our target, like our target power consumption level. But while we're powering up, we need to make sure we stick below 100 milliamps until we can get that 500 out of the host device, which again, we have to ask for. So we gotta be careful about that. This one's nice. I put this one on the playlist. Right now I'm just listening to Monster Cat's chill, like, mood thing. But I do want to eventually move to like a full-on playlist, because that will make it easier to not have sounds where people are talking to me in French. I don't mean any, I don't mean to be rude to humans in general or humans that speak French, but I don't know, I feel like having those voices on in the background is kind of not great when I'm trying to, like, and stuff. Oh. So not a lot of information about what, like, hardware we want to have here. Wish we had a bit more. It might be in the technical reference manual. Let me check that. Oh, okay, yeah, there we go. I think this might be internal configuration. MPS step-down converter and LDO voltage regulator. Some of these are talking about, like, internal connections, and some of them are talking about things that are actually accessible to us, and that can be somewhat confusing. Let's see, we're using the verify. Let me start using UFP pin out of this. That's this. So we've got 4 VDD supplies. I want to make sure this diagram is accurate. That's the battery input, and then this is the analog voltage supply, which is usually kept separate because it needs to be handled differently. There might be details about that in the ADC section. Got the cap. configuration. VDD LDO. Could really benefit from like an actual like full-on application diagram. Internal power supply for IOs, analog blocks. This is the battery backup voltage. This power supply must be connected to VDD when no battery is used. Good to know. Good to know, Chad. External power supply for the SMPS step-down converter. Power supplies and the other voltage supplies. When the voltage regulator is enabled, V-core is delivered by the internal voltage regulator. When the voltage regulator is disabled, delivered by an external power supply through the VCAP pin or by the SMPS step-down converter. I think we just don't have that in this pinout. Maybe our chip just doesn't have an SMPS converter. Looks like this specific chip might not have the step-down converter or the USB internal regulator, which is a little bit irritating to deal with because that changes how we look at the technical reference manual. Okay, so we have... It looks like we also don't have the EDD USB 33. Let me verify that. Stabilization for the main regulator is achieved by connecting an external capacitor to the VCAP pin. Specified in Table 14, 2 external capacitors can be connected to the VCAP pins. So we need to have 2.2 microfarad capacitors with an equivalent series resistance less than 100 milliohms. Let me take a quick look on DigiKey.
When you're calling out,
I'm calling out for the paradise. 2.2 UF capacitor. I have had bad results using DigiKey's like search function for this rather than just. So we need. Is it 2.2 microfarads? Take a quick look at this.
When you're calling out for a paradise,
Looks fine.
you won't need
20% tolerance. Sheesh. Is there any guidance as to the tolerance on this thing? Variation of plus or minus 20% is tolerant. Okay, so we're fine. So if I'm interpreting this correctly, what it wants us to do here and by the way, I don't think I've mentioned this before, but if you see me making a mistake, like something that's clearly a mistake, then please do point it out in chat. I will not mind at all. Alright. So, if I'm interpreting this correctly, what they want from us is 2 external capacitors. And I wish they just had like a sample implementation here. So let me take a look at this, and I guess we just need to kind of ignore. We kind of need to just ignore all these supplies that we don't have. So VCAP looks like it is being. It looks like it is just being connected straight through VDD. What is this diagram? Hey, this isn't ground, right? Because this would be connecting high voltage to ground, which doesn't make any sense. I feel like this is the LDO supply, which is a capacitor to VCAP. Our VDD goes straight through VDD LDO into our voltage regulator, which we don't have on our package, by the way. There is no VDD LDO. I'm assuming they're just saying the default VDD on our package is connected through here. Again, I wish there was a little bit more clarity. I believe the VDD VSS like way of describing these. VDD is positive, VSS is ground, but let me check real quick. E is positive and the S is negative. Okay, so VDD is positive and VSS is ground. Like, why? I must be reading this wrong. I don't know. Maybe I'll have to, like, send an email to ST Microelectronics about this, because, like, this diagram is somewhat confusing because it really does look like we're supposed to connect VDD to VSS here. Well, in any case, it's like we are supposed to connect the capacitor between VCAP and VDD. Which, again, VDD is the positive, just like VCC is the positive. VSS is the ground, just like G&D is the ground. I apologize profusely on behalf of the humans who came up with these terminology choices, but you know how it is. Humans are gonna human. I can just have 2 of these, right? I believe, based on my interpretation of that diagram, that this is the correct implementation of these capacitors. They need to be 2.2 microfarads. Let me specify that there so we don't forget. I'll just do a sneaky copy and replace that slash mu with an actual mu. It looks like KiCad has changed from leaving it a question mark until you specifically tell it to enumerate them to just giving them designation numbers by default, which is, I think, a reasonable choice to do, although we might have to be careful about, like, renaming our things. I believe some of these that were created in the old version still have the question marks as the designators. That being said, I think that all of these VDD supplies should just be fine to connect to the same thing. The analog stuff we'll probably have to handle separately. Again, I'm probably being over careful with this. We're not doing any like high frequency measurements where noise would be a huge issue. But I still want to be careful. If we do decide to do something that requires high noise measurement in the future, I want to be able to reuse this without having to totally redesign the whole analog domain. And also, it's just good practice, you know? Sometimes you don't think you're going to need something and then you end up needing it. And you're like, well, darn, I didn't design right for this, and I have to redesign the whole thing. Best just design it right from the start. Okay, also, VBAT needs to be connected to VCC. I'm just scrolling through here. I want to make sure that we are connecting those pins correctly. And there should be a description of how to connect the, how to do that analog domain here. Either up here in the description of the ADCs, which it is not, or it is down here. It might also be in the technical reference manual, so let me check there. It is irritating to put this in the technical reference manual when there are a bunch of pins that are discussed in the technical reference manual that just aren't there on our chip. I really wish they would have given like example applications in the individual device data sheets. Looking for a diagram. And of course, we'll get into this whole section of the datasheet later when we're actually programming the microcontroller. Right now, I am just scrolling through to see if I can figure out what the power connection requirements are. Frustrating that they make this information so hard to get. I know the 328p, the little 8-bit Atmel AVR microcontroller that gets used in all the Arduino Unos and Nanos. Let me slightly edit the crop on this a little bit. There we go. I want to make sure that no one's name is getting cut off. Okay, but that being said, I might just look at that if I need to. Ideally, I shouldn't. Ideally, they should put the diagrams you need in here. Look like we got it in here. Should include better application examples here. Although again, they should probably just put those in the data sheet, because if they did that, it would be more easy to see what's device specific. You can sort of see here the way that this works. You've got your core domain, which is like basically the CPU and some core peripherals. And that's sort of your main power domain. And there's some other stuff that comes off of like the VDD domain. And there's your battery backup, which goes through VBAT. And there's the USB regulator. There's this pin that we don't have, which would have allowed us to run the USB off of 3.3 volts, which isn't relevant to us because we already have 5 volts. And then the analog domain is totally separate. It's kind of like air-gapped, so you can run that at a different voltage level. Very confused about how the SMPS step-down converter like relates to this chip that doesn't have the inputs for it. Might be mentioned somewhere in the power supply management section here. Actually, I don't believe it does. Yeah. Two three 733 725 735 730. Yeah, this is describing the same thing here, but I really could use some clarification about what exactly it means, because this device doesn't have that step-down converter. start writing assembly. We'll get there, chat, don't worry. The SMPS step-down converter and the LDO are not available on all packets. When the LDO is not available, the SMPS supplies a voltage regulator and optionally an external circuitry. Okay, but what about when neither of them is available? Like, do we not have the we do have an LDO, but we don't have the step-down converter. Okay. So truly, this should be something they start, like, at the top before they explain what the SMPS does. We have an LDO, we don't have a step-down converter. Let's take a look. So what we care about, because we don't have the step-down converter, we want this, like, one configuration. Okay, there's like low power run modes there that get described here. I'm wondering if those are supplied specifically by the SMPS and we don't have them? The embedded voltage regulator requires the external capacitors be connected to VCAP pins. Okay, got main low power and off. Okay, no, so the levels are scaled by something else. Voltage regulator section in the datasheet. Voltage regulator section? Yes, we do. Okay. So yes, we do have these. This is here. We got it. Once we use this mode 1, and we have to connect this as appropriate for mode 1, although we don't have any like SMPS inputs. So again, this is extremely puzzling because okay, wait, there's no dot here, which means this isn't actually connected. Okay, so this capacitor actually goes to ground. I can read these diagrams. I truly hate that they're like two different conventions. One of them, this cross here means that it's connected. One of them, this cross here means that it's not connected. But no, this is the ladder here. So I was just misreading this diagram somewhat badly. So VDD only goes into this VDD supply, and then VCAP goes to ground. So I was doing that wrong. I'm glad I caught that. But only the ground, like, symbol is global. Go into the power options. Put that there. There we go. Now our microcontroller won't die when we try to turn it on. That's important, chat. You don't want your microcontroller to die when you try to turn it on. Oh, would you look at the time? Okay. It is 2:25. So I think that I'm gonna take my first break. Do you know what I mean by break, chat? Do you know what I mean by break? I mean Touhou break. Pause the emulation. Welcome to Windows XP. Hold on, let me real quick. Spell Touhou right, please. Let me see. There we go. Update the stream description. And we're gonna spend maybe like a half hour or so. This. Make sure that sound's looking good. Yeah, that's looking pretty good on my end. Alright, hit key. This is the first game in the Touhou series. I have played some of this game. I have not played any other Touhou. Oh wait. I've also played Luna Nights. I played this game and Luna Nights. Some of this game. I don't think I actually beat the final boss, but yeah. This Touhou game, somewhat unlike the sort of standard you'll notice that I'm running along the ground here, and it seems kind of like Breakout. So this ball here, ow, this is my only way. The goal right now is to break those cards. The only way I can do that is by throwing the ball at them. The ball will kill me if it hits me and I am not, like, in the right, state, as demonstrated previously. There are these, like, E-spheres going down. Those are extra points. You want to collect them. They're best if you collect them, like, all in a row. Yeah, we'll get to it, but this game gets a little bit more complicated than this every 5 levels. But for now, it's pretty simple. We just have to destroy all these tiles. There are a lot of... The controls to this game are kind of weird and complex. There are only, like... There's left arrow, right arrow, and then 2, like, action keys. But there's a lot of, like, contextual controls. When it says, bomb up, we have a super bomb, although I don't remember how to do it. I believe, it's like, yeah, that. It's hold left and right, and then press, Z to activate your super bomb. Which means that if you are pressing Z and you accidentally hold left and right at the same time, you will activate your super bomb. Z lets you fire these little items here, and X is sort of X while you're not moving does this little thing, and when you are moving it lets you sort of dash along the ground. There we go. Okay, it's time for stage 5, chat. Just in case you were worried that this wasn't a Touhou game, I can assure you it is. Ah! So we have to hit the boss with this, our funny spear and not get hit by the bullets. Which can be kind of difficult. Ow. Well. That's okay, chat. We can keep going. I wouldn't exactly call myself good at Touhou games. Just as a fair warning. Ah! Ow. So you'll notice that our funny sphere will break bullets, but you can't break bullets without the sphere. Ah. Melee attack. Let's use some of these super bombs. There we go. First boss defeated. Alright. Alright, chat. Here's a difficult decision we all have to make. Are we going to... it's a branching storyline. It's kind of like Shadow the Hedgehog. We can either go to heaven or hell. Last time I played this, just on my own time, I went to hell. But I think this time we're gonna go to heaven. Go. Totala? I didn't remember total being misspelled like that. Oh. Ah, I missed the P. Oh, we're gonna run out of time. Hurry up! Oh, this is what happens when you run out of time. Ah! Aw. F in the chat, we didn't even get on the scoreboard. Fine, we'll do better this time. Almost there. I'm carrying up. I gotta just get one more. Calm down. Ah! Ah! Oh. There we go. Okay, perfect, perfect, perfect. Don't worry, it was never any issues. And you'll note the amount of points we're getting from each P is higher now because we haven't missed any. It's like the longer your streak, the more points they're worth. Oh, you have to forgive me, it's a little bit hard to provide commentary while playing a solo game. Calm down, we're fine. Oh, goodness. Ah! That was accidental. Oh well. Oh, goodness. Oh, I don't like this layout. Oh, scary! Okay, there we go, there we go. We're fine, we're fine. What? Ah! No, the pea! The pea betrayed me. Yeah, it's so hard to do those, like, tight turns without accidentally super bombing. Okay, stage 10. I have not seen this boss before, and I immediately beefed it. Oh. Okay, we've got eyes. Ow. Well... missiles! Oh, that's extremely good. Ow. Oh, expect a lot of retries on these bosses. Oh, goodness. Okay, so are the eyes? Okay, no, the eyes can... The eyes are the weak point. Ah! I really gotta get better at using super bombs during these. Carefully. Scary. What are we supposed to be doing about that? Oh, okay. It doesn't go all the way. Oh, yeah. Ow. Well, it'll be interesting to see what that attack is next time we get there. I think after this boss, I'm gonna go back to soundboard design. Risky to get the, it can be risky to get the ball far away from you, but it's also risky to have the ball close to you, if I'm being honest. Ow. It's okay, chat. We're getting better. We're getting better. I definitely feel much better at this than I was last time I played it. I'm accidentally super bombing a lot less. Ah! Ah! She says, immediately beefing it. As you all know, I'm great at video games. Okay, that does kill me. I wanted to try that out and see. Maybe it didn't. Maybe it didn't. I would have more freedom at the start. But no, it does, in fact, murder us. Okay, carefully, carefully. What? Well, that was just mean. Is those missiles, you can't break those with the sphere. Okay. Oh, it is so hilarious that they just fire missiles at you. Not even like magical energy bullets or whatever. No, they're just shooting missiles at you. This is heaven. Honestly, I feel like this is worse than hell. Ah! That is really difficult to block. Or like move it around like that. I don't know why they call this game highly responsive to prayers. It's never responded to mine. Ah! How do you get past that? Oh. I could have avoided that. You know, when Pancake told me about this game, she told me it was just like Breakout. As you can see, this is really a Breakout-like at heart. Like, no, it's not like a Touhou game. It's really just, it's a really weird one. It's more like Breakout. Ah! I can't do anything about this. I can't, like, dash through that. It's like, ah! And I gotta keep an eye on my health. When I say health, I mean lives. Oh, stop with the missiles! I say, as it turns out, the ball is actually the real threat. Okay, I need to, like, move in the... I need to, like, be aware of where that one's moving. I can dodge it like that. Okay, yeah, there we go. Ow. It's okay, we've learned something. We've learned how to dodge that attack, as long as we're, like, in the middle. That one moves out before that one moves in. Ah! Okay, now what was that about? Oh, this isn't good. Okay, it's fine, you were fine. There was never any danger. There we go. Come on. Hard to control the sphere. Yeah! Oh, what is this attack? Ah! Okay, we're back to this attack. Oh, rip my life. Unfortunately, it's invulnerable during this stage. Oh, that's right, I can, like... I've forgotten the exact thing you need to do it. It's like... Ow. You can, like... Ow. Is it? I think it's just this attack that can... Yeah, this attack can deflect some bullets. I don't know if it can deflect the missiles, though. I think it can't. Ow. Oh. Why do I always do this to myself? Okay, we're doing this now, huh? Oh, I don't actually know what this attack is. I've never experienced it before. Oh, no. Okay. Okay. Ah! Okay, this could be worse. This could be worse. This attack could definitely be worse. Come back, please. I need you. There we go. Ow. Okay, I almost got it that time. I almost got it that time. We're making progress. My prayers are being responded to. Ah! I could have easily dodged that, but oh well. Carefully. Carefully. Ah! Oh no, this one's bad. Oh well. Stop firing missiles at me, please. Okay, yes, this attack I can deal with. Thankfully, that character in the center of the screen has lines that are about where you need to be for the laser attack. Ah! Okay, okay. I believe, chat. This one's gonna be the run, chat. Ah! This one's gonna be the run! Ah! Oh no, why am I being attacked with this now? Oh, that's new. As usual, you are absolutely invited to let me know if the audio or video is bad at all. What? Come on! That one was a little bit unfair, don't you think? Ah! Ah! Ow. Well, we're really not getting in the hits we want to be getting. Oh, come on. Ow. That one! Oh, come on! That one I could have done. Oh well, back around we go. Okay, missiles time. Ow. Ah! truly love the use of missiles. I mean, I hate the missiles mechanically, but I really love that they are here. I really love that this is a common spell. That being said, I hate them mechanically, so please do skip this phase. Thank you. Ah! Fine. Doing great. Doing perfect. Gotta get that one. Ah! Come on. Ah! We were so close. It's okay, chat. It's okay. We'll get it next time. This one's gonna be the run. This one's gonna be the run. I can feel it in my soul. About it. Ow. Okay, never mind. Actually, you don't want to do this anymore. Skip this phase, I don't like it. I am fine with this phase. Come on, get those hits in. Ah! Oh, I gotta be careful with the spear. It's okay. This run is actually the run. I was lying last time. I'm sorry, I know I shouldn't lie to you. But I was lying last time. This run is the actual run. Ah! What? That doesn't matter. That's just a stumbling block on our way to inevitable victory. Okay, we're fine. Huh, you thought I was gonna die there, didn't you, chat? Well, I died there instead. Okay, stumbling blocks on our... You didn't see that, chat. This one's the run. Just tiny stumbling blocks on our way to inevitable victory. What? Unfortunately, if I'm not mistaken, you can't do that little, windshield wiper attack against the missiles. Ow. That's okay, we skip these phases. Never mind. This one's the run. Actually, this one's the run. The last one wasn't. But this one is. There we go. No worries at all. Oh, I really despise this phase. Ah! We are fine. We are not fine. It's okay, chat. Those last times I was lying. This time, I promise this one's the run. We're gonna really do it this time. That one is just to keep you on your toes. You know, if I just don't get hit golf, which I am totally capable of doing, then there wouldn't be any suspense. You know, if I wasn't on my last fight, you know, where's the suspense? Where's the surprise? Gotta keep the humans on the edges of their seats, and you didn't see that. Okay, maybe this one isn't the run. But it might be. Listen, it's gonna be soon. We already got that run where we almost got there but died right at the end. It's only a matter of time now, chat. Ow. Ow. Sometimes your sphere is your own worst enemy. I think they were in a song about that. Stop doing that. This isn't helpful. That is not a helpful place to bounce. Oh god, more missiles! Okay, we're gonna skip this phase. We're gonna skip this phase. Okay, we're in the... I mean, not the last phase, but the last phase that we want to see. We just need to get 2 more hits in and then... Oh, never mind. If we got 2 more hits in, I could have super bombed, and that would have taken out the other 2 health. Okay, don't worry, chat. By the way, if you're wondering, I am, in fact, using the, Merry Christmas Windows XP theme. Oh, this window doesn't like being moved around. Hold on. Minimize it. I am using this Windows XP theme. Which, if you remember a long time ago when we first started doing the shareware games, was one of the ones we discovered. Oh no! Oh, the rockets! Oh! Dangerous, dangerous, dangerous! Ow. I gotta say, I feel like that's the most dangerous attack in this fight. Oh, you love to just absolutely beam yourself before the fight even starts. What? Okay, this one... That one was maybe a little bit cursed from the start, but it's fine. A lot of this feels like it's like luck of the ball, you know? Like, I don't know, maybe there's a way to be more in control of the ball than I am, but... A lot of the times it seems like it just, like, moves with a mind of its own. Come on. Nope, 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 It's okay, chat. We'll just skip the next rocket phase. Come on! Come on! What the fuck? Ha ha ha! Okay, as promised, skipping the next rocket phase. And we can skip the first half of the lasers as well. Ow. She says, not quite going far enough to the left. It's okay, we're doing it, chat. We're making it happen. Oh, that's right, I can shoot these bullets. I gotta remember that. So we can't damage the boss, but we can damage the bullets. What? Carefully. That one seemed a little bit excessive. That one seemed a little bit... That's also a little bit unresponsive to prayers there! Insufficiently responsive to prayers. Okay, we've managed to save our super bombs a lot more effectively this time. You know you can do it. Okay, okay. And... yeah! Oh. Victory. Oh, Totla, my beloved. Oh, I hope my expression of happiness didn't clip the mic too bad. But okay. Okay. A very invigorating Touhou break. Let's get back to it. Okay. Where were we? We had figured out the correct way to apply these capacitors because I had been severely misreading this junction point here in this diagram. So because it seems like this technical reference manual doesn't have an example, you know what, let me see if there's like an application note they put out. Oh, I still got something happening. Let's turn that off. Back to the category. Hey. No. There we go. Back to the right category. PM32H7. There we go. Okay, this is probably gonna list what to do. Ah! I've been kissed by Pancake. Pat, this is an emergency. I think she's heading out. Pancake! Okay. There we go. Use of a single solid ground plane common to analog and digital sections is recommended. Place a capacitor very close to the ADC input pin is recommended. 47 picofarads is a good starting point. They're really kind of allergic to actually putting diagrams in these things, huh? Well, let me actually show you the 328 PB datasheet. Oh, I just by instinct pulled up the one for the PB because I use that more often, but it'll be the same situation. So a much more brisk 400-page datasheet. That's just because this thing has fewer features. It is quite a lovely little chip for what it does. Somewhere around here they should have... Yeah, there we go. They actually have board links. So how to set up your analog section. You see, this is what they recommend as your input circuitry. I like this. This one's going on the playlist. So this should probably be on here if it's not already. Yeah, I like that sort of situation much better. Where they've put specific diagrams for you to work from. That being said, unlike the 328PB, which recommends a separate analog ground plane, this microcontroller recommends a single ground plane. And just to be clear, a ground plane is having a layer on your PCB that is just like a solid connection to ground. It's like a solid chunk of copper that connects to ground. The ADC voltage source must be placed close to the microcontroller, and the ADC input tracks must be kept as straight and short as possible. They must have a ground plane on an adjacent layer. Adding ground shielding around ADC traces is also recommended, with sufficient vias between the shielding and the ground plane. Now, a lot of this we don't necessarily need. Because we're not doing a lot of high frequency sampling. We don't really care about sampling really quickly. It doesn't even have to be that accurate, because all we're using the sampling for is to check the voltage level. But again, like I said, good practice. Decoupling capacitors should be added between the digital voltage sources and the analog reference voltages. VREF plus and VREF minus kind of define the upper and lower limits of what your ADC can measure. Excuse me. So if VREF plus is whatever VREF plus, human words. Whatever VREF plus is, that ends up being the like highest voltage you can measure. So that's your like, when the number you read from the ADC is the highest, that means your voltage is at VREF plus. And when the number you read from the ADC is the lowest, that means it's at VREF minus. So if we had a specific voltage range we wanted to measure, we could set VREF plus to be only like 1 volt if we were getting a signal that was between 0 and 1 volts. Or if we had a signal that was like between 1 and -1 volts, we could set VREF minus to -1, I think. It depends, it differs from ADC to ADC, and there might be some offsetting that needs to be done, but that's not really relevant for what we're doing today, so we don't have to worry about it. I have to pause the emulation. Oh no! Xmas save caused an access violation. Oh. The save. Pause the emulation here. Where were we? at the general application note here. It's irritating that they have so many like different documents for one microcontroller and they don't just like stick this in the technical reference manual. Oh, is there a... there is, but it's not here. I have to go look it up. They're using those microcontrollers that turn blue and lift off the board. See if we have like... So you say we should use this as a base, but you don't make it easy to find the actual design here. Hardware layout, yeah. That's fine. This is also a configuration that has the SMPS, so we have to like make changes because we don't have the SMPS. But oh well. How expensive this evaluation board is. $344. Y'all gotta have some more minimal designs for this. I really just need like a breakout I can play with on a breadboard. Okay. Inputs. No, it's you don't. Okay, maybe it's like somewhere in CAD resources or something. Okay. Let's see. Alright, let's take bets, chat. Are these gonna be in a format I can't open? Are they Altium files? They are in fact Altium files. Okay, I can't open these without showing my real name. It would be really nice if you had like PDFs of this stuff. Oh wait, there might be PDFs up here. Okay, there we go. Oh, feed on stream, feed on stream. Get the PCB layer. It'll be like around An actual, like, PCB drawing would be very, very nice to have here. Well, that's a PCB drawing. All things keeping me up. Why are these just XL? This is made by this ST Microelectronics. Whoa, this is from 2026? Holy crap! I got designs from the future! Yeah, we gotta like hide that. Can't let the humans know about non-linear time. Okay, so I guess I should probably look at add resources, this top board schematic. It's where that they're using buses for some of these signals, but they're like breaking out some other ones. Oh well. Yeah? Little pictures there? Why would you do this? Guys, you gotta like put some information on here. Okay, I guess I am going to like open Altium so I can see these files. Give me one moment, I'll be right back. I can bring Monster Cat back here. Okay, give me just one moment. I will be right back. Altium's gonna take a little while to load up, of course. See, the reason I'm not using Altium for this project is because not everyone has access to Altium. I mean, technically I'm not allowed to use Altium for anything other than, like, school projects either, so, you know, I'm not doing that. But it would be really nice if they'd, like, exported it in a more, widely usable format. Makes it much easier for hobbyists. I hope everyone in chat's having a nice day. It's a lovely, extremely rainy afternoon over here in Chicago. I can look out my window right now and see some... They're not exactly skyscrapers, but they're pretty tall buildings. Lost in the fog. It is quite lovely, but the last thing I would want to do is go out in that weather. Let's see, what temperature is it? Let's take a look, chat. It is currently a brisk 43 degrees out. And rainy. I hope everyone's in chats having a wonderful day as well. LTM Designer is still loading. really likes to take its time. But what are you gonna do? There we go. Still be able to open this read-only, right? Not actively signed in because I let the license lapse because I'm not using it at the moment. Let me get viewer license. Don't show that on screen. Well, I am glad that I did that. I'm glad that I'm on a different screen right now, so you can't see that me. And we open the PCB project. Messages. And the funny PCB document. The right PCB. This is the camera module. Okay, let me go find the right PCB document. Yeah, it's looking that way. Get on with this other one. Once again, apologies for the delay. I do want to do their reference design, and unfortunately they didn't think to actually break out that PCB to a PDF, so... Yeah, this is absolutely the camera. Okay, fix that. It would be really nice if these things were named descriptively. This is... God, what is happening here? ST, what are you doing? Well, in any case, this does not look like the full board. For exactly what component it is, but I'm gonna have to check another one. Is it MB1331? Okay, well I opened MB1331 and it isn't that. Oh no, that's 1379. Okay, hold on, let me get 1331. Could have been done better. Okay. There we go. That looks much larger, and now we should be able to open up 1331-DO3 1331.PCB dock. There we go. And that should be the main PCB. And then I'll switch y'all back over so you can see. Just a moment, it has to update its polygons. Oh yeah, that looks about right. There's a couple of new pages, and let's bring y'all back over. Welcome, welcome. Welcome to this. Okay, so what do we got going on over here? So they are using a BGA component. So how many layers do we have on this PCB? 1, 2, 3, 4, 5, 6. Okay, cool feature of Altium that KiCad also has. You can this thing in 3D. Ooh, isn't that cool? 3-dimensional. Best compliance. Ah, it's got a little Wi-Fi module on there. Huh. Neat. Look at what they've got going on over here. Actually, best not to do that in 3D mode. Using some interesting designs of the solid bits here that are named like this are just like planes of copper. So this is the SMPS. So this stuff is all like SMPS supply stuff. So like this stuff here. Oh man, I want to have my hand tracking set up so I can like hold my hand out and demonstrate things like this. Like that, but that bit right there is the SMPS input or the SMPS output. Huh, that's interesting. I guess it's using that as like a board supply situation or something along those lines. I can also open the yeah, let's just close this whole project. Open the actual board project here. There we go. Okay, and that is the board power supply. This is specifically the power supply to the microcontroller, so this is more interesting to us. Got a bunch of decoupling capacitors that aren't really well labeled where they are. Let's see, C123 is... I don't know if Altium has a feature where you can just like pull up a component based on its reference designator. Let me see. If I like right click on this, can I... like it's in here. Oh, this pulls up the data sheet. Oh, Lamal, they have this hosted on their like private thing and it just pulls it up. I think they could just use like a public link or something. Oh well. You know, they say that this is like the gold standard that everyone should use as a starting point for their designs, but it really is a very complex thing to tell people to use as a starting point. Let me see. If I could tell at a glance which of these pins on the bottom were which, the issue is, I don't know. I would have to like look up the datasheet for this part number in this package. Yeah, I'm thinking what we're gonna do is we're just gonna do our best, and it would probably be fine because we're not doing much analog stuff. Certainly not like high frequency analog stuff. So we're just gonna close this out. I'm not gonna save the changes because I don't have a license at the moment. But it will not let me save those changes. Okay, so we want to have decoupling capacitors on all these lines. Unfortunately, they're a little bit close together for me to display that in a rude way. Maybe I'll like run them out here and put the capacitors there. Wow. Sorry for being away from the microphone for a moment. Okay, this is nonsense. Typing in the PCB routing guideline. Configuration that can be used is 4 or 6 layers stack up. 8-layer boards may be required for very dense PCBs. So they really want us to use a 4-layer PCB minimum. They want us to run high-speed signals on the top, have an inner ground plane and power plane, and to write. So the ground plane and power planes they want to have on the inner layers of the PCB, and they want the high-speed signals to go on the top and bottom. Adequate power decoupling for the microcontroller is necessary to prevent excessive power and ground bounce noise. Following recommendations: decoupling capacitors as close as possible to the power and ground pins of the microcontroller. Let me like grab the link for this and like put this in the old Obsidian. I should also copy this information in here. Go into our downloads folder. AN5307. Oh, hello. Welcome back, man who whispers to me in French. That's so true, dude. That's extremely true. I don't know any French. Sorry. Okay. Place the decoupling capacitors as close as possible to the power and ground pins of the microcontroller. For BGA packages, it is recommended to place the decoupling capacitors on the opposite side of the PCB. Add the decoupling capacitors to as many VDD VSS pairs as possible. Connect the decoupling capacitor pad to the power and ground plane with a wide and short trace/via. That all makes sense. We'll also want to look at this section because we are going to be using an SSD card. table of contents at the end. It's so weird. Stop breathing at me, French guy. We know where to begin. I don't believe we get this pin broken out, unfortunately. Gotta say, I am becoming less and less impressed with ST Microelectronics documentation here. Like, there's a lot of, like, documentation that works fine if you have the microcontroller with all the features, but, like, the second you have, like, one of the microcontrollers that the datasheet describes that doesn't have all the features, then suddenly it, like, doesn't tell you what's up. You know, it doesn't tell me what to do with the power supply when I don't have the SMPS component there at all. One moment. Okay, so we are getting external component recommendations, which is good. Tied to VDD when this pin is not present. Okay, yeah, that's reasonable. Not relevant to us. Not relevant to us. Also not relevant to us. Also not relevant to us. Those are just the VDD pins. As long as we shouldn't turn on the regulator because we don't need it. We don't need to worry about that. Connected to VDDA through a resistor. Tied to the SSA. I don't know why they even break out this pin in our package if we just have to tie it to the SSA. Oh, hey! that's more frickin' like it. That's what I want to see here. Thank goodness. They certainly made us dig to find this. Okay. So this diagram is what I have been looking for. Actually showing me, hey, this is where I should put the capacitors and where they should be, like, in a visual representation. Like, text is great, but some of the ways they've described them are a little bit ambiguous as to, like, where the capacitor should be and what configuration it should be in. This, on the other hand, is unambiguous. Okay, so... Okay. So now we can start actually laying this out. I'm a little bit more confident in exactly where to put everything. So our LQFP100 pinout, you will note, has VDD connections, but it does not have the special LDO VCC connections. I believe it's just tied to the it's just straight up tied to the LDO internally. At least that's my understanding. Although it probably does mention it around here somewhere. VDD LDO. No, it doesn't. It doesn't actually mention it here. Oh, thank you, ST Microelectronics. I really appreciate your detailed documentation. Okay. We don't have the SMPS. We do have these VCAP pins. A 2.2 microfarad and a 1... Oh, no, this is... If the LDO is enabled, we need a 2.2 microfarad capacitor there. Yep. I believe that is what we did. Yep. And again, this is not connected externally, so we don't need to worry about it. I also don't think we have a PDR on pin. Like, they're really skimping on the pins for this package. But it should be fine. Internally tied to VDD when this pin is not present in a specific package, so yeah. And this is also not broken out. So our VDD pins should each have 100 nanofarad capacitors and then a 4.7 microfarad capacitor as, like, in parallel with all of the individual capacitors. Alright, so let's get that going. So the 100 nanofarad capacitor is what we want for this. I'll do it. And I could just do it in the same way they did it, but again, I find that like a little bit unhelpful in terms of like being clear about what's connected where on the schematic, I really think is helpful, especially when you're doing open source hardware, to like be very clear about what's connected where on the schematic to make it easier for people who you know, can't necessarily just send you a Slack message to work with your design. Of course, if you're in like a company environment, it doesn't matter as much because people can just like, you know, send you a Slack message. Okay, then we just duplicate these. One is slightly farther than the others. Let's fix that. And how many of these lines do we have? 1, 2, 3, 4, 5. More. Capacitors are all to ground, it looks like. Place multiples of these. Place repeated copies. There we go. Okay. Here. Actually, just tie all of these together. Point. This is mostly just like a visual representation of what the PCB layout will look like. These all will turn into basically the same net, but having it laid out on the schematic in a similar way to how it looks on the PCB should be helpful for people who want to, you know, replicate the design. And then we need a 4.7 microfarad capacitor. Place this one out a little bit of distance to sort of indicate that it's separate. To be a little bit prettier. There we go. All clear the ground, and we put BBB through here. BAT is connected through its own series of capacitors. That's 1 nanofarads and 100 nanofarads. Let's actually move this over here. Get one. Back there so we can fit the back over. Nanofarad capacitor and a 1 microfarad capacitor. Clear that way, I think. Actually move all of this like section. Out the PGDA when we need it. I can
tell me stories underneath sunsets. Could it be more than just one night? Kissing the cab ride, head turning left, right. Get a ticket for two to wherever you choose. Drinking some red out of the blue. You say my name with your accent, makes me remember how much I missed you. Hope you're planning to stay for a million days. You'll be my summer in December. Hey boy, trust my intuitions always. I'm not superstitious, I got lucky. Stole your heart and it was mine for the taking. It was mine for the taking. It was mine for a million days, in a million ways. Stole your heart and I got lucky. Stole your heart and it was mine in a million ways, for a million days.
I'm just trying to tidy this up a little bit.
I'm bad at pretending, you know I'll be true. Sunday mornings and midnight lights turn into songs that you watched me write. Stole your sweater on that night. You took a picture, I keep by my bedside. So you're mine when you're gone, baby, please don't be long. I got my ticket to the west side. You say my name with your accent, makes me remember how much I missed you. Hope you're planning to stay for a million days. You'll be my summer in December. Hey boy, trust my intuitions always. I'm not superstitious.
I think part of my goal with this project is to create some nice reference designs for people who want to work with these microcontrollers, which is why I'm taking a lot of steps to like label things and like put graphical boxes around stuff so that you can tell clearly what's going on. put that like 2. That's better. 2. Like I said, all this is going up on GitHub when I'm done. Okay, and this bit, we do want to pay attention to this VDD50 USB. We don't have a USB, or a VDD33 USB. It doesn't exist, so we don't need to worry about it. We have 4.7 microfarad capacitor on VDD50 USB. We verify that that's correct. Grab the USB one out. I wish they would like put that somewhere specific so I don't have to go digging around in the alternate pin function table. Oh well, to EA9. Again, I'm checking over things as I do them just to make sure that if I make a mistake I catch it. Why are you doing this in this order? Oh yeah, there it is. VHSV bus. So I'm assuming that's VDD USB 5.0. That's my assumption. Wait, what is... Hold on, datasheet? OTG HSV bus. The only place it shows up. Okay, so we're just gonna assume that that's VDD50 USB, and if it's not, well, I guess we just die. Here lies twitch.tv/digimint. He died in a tragic, badly documented microcontrollers accident. This out here. It should hopefully not be too cluttered to drag that out there. I do want to show this decoupling circuitry effectively. 0.7 microfarads. On stuff we should do for the USB pins? I don't think so. We will need to look at the pins for the SDMMC interface, which we'll do, I guess, later today. VDD50 USB. Okay, what else? Our analog domain. So we're just going to use VDD as our 3.3 volt reference. I don't see much of a reason not to. But I'm liking quite a bit as well. I'm actually not sure if VDD50 USB is the same thing as OTG HSV bus. Let me see. We probably have somewhere around. OTG HS. In descriptions. There's OTG HSV bus. Yeah, I guess that's just what they call it in this set of the family, which I really, really wish they described better. But that document go. Lost the document chat. Oh, there it is. I just missed it. Scrolled down too far and forgot which document it was. ST Microelectronics color scheme is similar to what Atmel's used to be. Like, that shade of blue made me think this was the 328PB microcontroller datasheet for a moment. put a little annotation on these to indicate that they should be close to the pin. We got the USB regulator, and VDDA is also going to need its closed capacitor. And I'm going to write a little note down here. Just have the thing where I can, like, symbol view. No, that's not. Is there a way to set, like, field text variables? Let's see. See, Altium's nice enough to have like schematic label variables on here, but I might have to write them myself. Feels like that shouldn't be how you do this. Oh, there we go. That's what I needed. Double click on that. Okay. Title. We actually use the name of the microcontroller. Any there we go. Actually, I think it would make sense based on where that field gets placed. There we go. Like I said, want to make sure that this is good documentation. Do we do anything special for that? SSA can just go directly to ground. Good stuff. So we'll need a VRF plus. Do we not have a VRF minus on this package? Like we might not. Oh, it happens. VRF plus goes to 47 ohm resistor from VDDA. Right, so let's I want to just put the whole microcontroller a little bit to the left. By the way, you might be noticing that depending on which direction I click, like if I click and drag down and to the left, what gets selected is different from if I click and drag up and to the right. And that's because dragging to the right will only select things that you have fully included in the selection, that are all the way in the box. Whereas dragging to the left will do anything that even touches the box. And that's generally like standard practice in PCB design tools. Just connect this to cable. We've got handle that over here. Bring the VRF plus out here. Now we can have our VDDA, which we want to connect to our normal power supply, 47 ohm resistor, the VRF doesn't need capacitors, you said? Yeah, or connected to VDDA. That is VRF bus regular. Take a look at that. That might actually give us more range. Let me check. When enabled by the ENVR bit in the VRF bus control and status register, VRF Plus is provided from an internal reference buffer. The internal voltage reference buffer can also deliver a reference voltage to external components through the VRF Plus VRF minus pins. Like a bit more information on what kind of voltages we have available though. Section 2, VRF. Internal voltage reference buffer supports 4 voltages which are configured with the VRS bus or VRS bits in the VRF bus CSR register. VRS equals 000 gives us a voltage of around 2.5 volts. I would like maybe a little bit more precision if we're using it as like a reference point for our EDC. ABC and DAC peripherals are not compatible with this voltage reference setting. truly fascinating decisions here. Okay, so what I'm seeing here is that we don't really need to worry about it. We have enough resolution on our ADCs that we can just have the 3.3 volts coming in, and because we're just measuring the USB control logic block voltage, we don't have to worry too much about it. Let's see, grab VCC 3.3. Put that here and rearrange once we're done. And then we need VRF plus, and we want a VDDA. Plus. And VDDA. And we'll start out with the circuitry for VDDA is somewhere. VDDA, 1 microfarad ceramic and 100 farads as close as possible to the pin. VDDA can be connected to VDD through a ferrite bead. Huh. It would be nice if we had like more information on what kind of ferrite bead we're looking for. Check the reference design. I believe I still have the PDF up somewhere. Maybe I don't. But I can. Whatever. Downloaded, don't I? Did it download? One moment, chat. I just have to dig up this of information. Yeah, that is. I don't think this is. To see the analog supply information for somewhere. Looks like right now in this document. It doesn't. Okay, well, time to look at documents until we find the right one. I definitely did open some of them. Oh well, let me search this so we can get back to the page. There we go. Alright. CAD resources. One of these schematic packs. It will be the 1331 will be the whole thing. too. Looks like they do put some like resistors here. Section should be near connect. MC. Or see where that goes. Just has a capacitor on it. Gotcha. They do it that way. So put in the capacitor here, but oh well. So 3v3 MCU, this is this a 600 ohm ferrite bead? Is that what they're talking about? Verify. I haven't used ferrite beads before, but I'm not sure if their symbol is the same as the inductor symbol. Okay, it looks like people are using inductor symbols to represent ferrite beads. Like, this is the actual symbol for a ferrite bead. It's looking. What else? I might not be fully. Yeah, there's a couple of different standards. There's a lot of different standards. The schematics I've seen in reference schematics use the symbol of an inductor as the symbol for a ferrite bead. Okay, yeah, so that's what it's talking about there. I think they would use like a specific symbol for the ferrite bead. But oh well. Looks like this is 600 ohms at 100 megahertz. So yeah, this component right here should do it. BLM 15AG601SN1D is BLM 15A. What? Oh, there. BLM 15AG601SN1D. Difference. Rated for higher current. So the one we have is rated for lower current, it looks like. Okay, so, yes, it looks like we are supposed to use a ferrite bead here. See, this is why we gotta be careful to, always look carefully into what we're doing before we do it. If we're not, careful about it, we might miss that ferrite bead, and that would hurt our ability to parse signals. It would probably work. It just wouldn't work as well. Okay, VDV through a ferrite bead if VDVA wants to be 1.6 to 3.6 volts. Okay, so we're so we need a ferrite bead. So we have this ferrite bead here, and then the 100 nanofarad capacitor, and then the extra 1 microfarad capacitor. Connected to one of the VDD pins. Okay, now the diagram showing it. I did it. Okay. 1 microfarad ceramic and 100 nanofarad as close as possible to the pin. I'm interpreting that as wanting both of them to be close to the... Well... Could definitely be better explained. We'll just go ahead and mark both of them as close to be safe. Well... like only the 100 nanofarad should be necessary to be close. Oh yeah, let's do that. So 1 microfarad ceramic doesn't need to be close, 100 nanofarads does need to be close. No, don't do that. That sort of fits more with what it has been. So... where has Baba ended up? There you are. Baba is a very good Baba. We put that there. And VREF plus the VDDA tool. We do what if it's 0 ohms? Bizarre. I guess they're probably not using the resistor method anyway. Just glancing at this, we shouldn't need these if we're connecting through the 47 ohm resistor. Got around here. Compacts a little bit. Over there. We do 0.2 width style dash. Having all these labeled boxes like this makes it easier to parse what's going on in the schematic. So, got BGDA VREF Plus. I believe we've handled all that. We already know. There's a the digital core in the CPU domain. That's interesting. Backup domain, voltage regulator, we don't have an SMPS. Reset and power supply supervisor. Devices have an integrated power on reset, power down reset circuitry, which ensures correct operational startup from 0.71 volts. That makes sure the device doesn't try to turn on when the voltage isn't high enough for it. Most microcontrollers have something like this. If we wanted to run this device at less than 1.71 volts, we could disable this thing. But then we'd have to do our own reset circuitry, so we don't need to worry about this. This is only for our, this is only if we wanted to run this on a very low voltage. At 3.3 volts, the internal system can handle it. Supply ranges, which never go below the 1.7 volts, are managed more efficiently using the internal circuitry thanks to the fully embedded reset controller. Yep. Programmable voltage detector can be used to monitor the power supply by comparing it to a threshold selected. Not really relevant to us. That's if we wanted to be really careful about our power supplies, but I don't think we'll be that constrained. Just clock stuff. We're not not going to be using an external oscillator, so the circuitry shouldn't be particularly complicated for us. But if we did, we'd want to look carefully at this section to make sure that we're using the right kind of regulator and such. So I don't know, it says that using the external oscillator is a good choice for accurate USB peripherals, so maybe we should do that. Huh. A very accurate high-speed clock is needed. Okay, wait, this is an internal 48 megahertz clock. High precision clock for the USB with clock recovery system. So I think we're still fine. I think we're still fine. We might still want to do it. Interrupts, don't you worry. Clock security system. So this is like, if we use an external clock as our like main system clock and it fails, there's something, there's hardware in the microcontroller that can like detect that it's failed and switch back to the internal oscillator. And if that happens, it'll give us like a big, it'll raise a big alert that we can use to like figure out what happened, basically. Well, not necessarily figure out what happened, but like respond to it. I think we should be fine with just the internal oscillator. I don't know, I strangely described it that way, as like the external oscillator is a good choice for a highly accurate USB peripheral. And like, well, how accurate do we need? Like, what's the difference? Is the difference significant enough that I need to like worry about it? Probably not. We might not even need to use high speed anyway. This also sounds nice. Let's add this to the playlist. This is all boot mode connection. The boot pin, boot base address. Let me take a quick look at that, see if we get that broken out on our end. FP100, we do in fact have a boot pin. That's Budo. That's good to know. Let's see. I guess it sounds like we can just connect this to ground. Or possibly, you know what, let's put on a manual switch. Put on a manual switch. Just in case. You never know what you're gonna want. I'll just connect it to a single dip switch. If I happen to want more configuration, I can add that later. Okay, so Budo. And left align it, put that right there. Resistor. Good value for a pull-up resistor, chat. My brain's telling me like NK. I'll look it up just to be sure. Because this is my first time working with this microcontroller, if ever I'm not sure about something and I can make it so that I can just like select between all the options on the fly, I should probably do that. I don't want this. Oh yeah, 10 kiloohms is normally a couple times smaller than the input impedance of the pin. something we can check on this data sheet here. Switch. Our EDP characteristics. Key characteristics. Import characteristics. Let me see. Oh, well, I guess we can just look here. Big pull-up equivalent resistor is typically 40 kilo ohm. Weird that I can't get the input impedance from here. But I think 10 kiloohms should probably be totally fine. And if not, what are you gonna do? I can just desolder the resistor and put on a better one. Okay. So now we can use this switch. I explained last time what this pull-up resistor setup does, but this is your sort of standard way to connect your standard on-off switch. Okay, to figure out what to do with the reset pin. Probably want to have a reset button on the board that we can use. Would you look at that? Okay, wait. Let's put a 10 kilo ohm resistor between. Oh. Well, if that's the case, I should probably implement that because that's what they say to implement. Okay, so that's an SPDT. Look at that. That there. And we do still need that 10 kilo ohm resistor. Put that in there real quick. Also not quite there. There we go. Ah! Happens here. Do that instead. Okay. Scan this box out by one. There we go. That'll let us select the boot mode. The bootloader code is located in memory. This is the hardware equipment that connects the host to the application board. This is made of 3 components. A hardware debug tool, a JTAG or SW connector, and a cable connecting the host to the debug tool. Real wire debug ports. ARM standard debug port that combines a 5-pin JTAG DP interface with a 2-pin serial wire DP interface. Let me see. So the debugger that I have right now, I'm gonna go real quick dig through my toolbox to look for it. But basically, Atmel, before they got I might the hair debugger is called an Atmel ICE. It is specifically designed to program their AT-SAMD line of devices, but I believe this is just a standard ARM debug interface, so it should be fine. And yeah, I have this teeny little debug port. 10-pin debug port. But yeah, I should be able to just program it with this. I just have to put the right interface on it. I have to put the right jack on the board to connect to. Go to the reference manual and WJ debug port selection. Gaming indeed. Welcome, Pancake. We're doing the special kind of gaming where you're figuring out debug ports. Okay. And connect the in. The port I have right now is only a 10-pin connector. Take a look. Well, I wish that the box that came in for me had this guy on the front. I really do like this guy. Humans should really put cool robots on the boxes for their microcontroller products. I think it would make things much better. Hold on, I'm going to go ahead and put... One second, chat, just 1 second. Put him up there real quick. I can probably chroma key out that background. Is there a way for me to... Yeah. Truly an incredible guy. Hold on, sorry about the detour, chat. We'll get back to our previously scheduled programming in just a moment. I just need to get a sort of average color here. The hex code there is 437E6A. Drop that into OBS real quick. Are you sure that's the color? Oh wait, I clicked on it twice. Okay, there's the actual color. That right there, that'll do it. There we go. Fix that and fix that. Not quite. Well, we won't worry about it. He's allowed to have a background. Stick him right up there. Okay, that being said. AI background remover sites. I'll worry about it later. I'll worry about it later. I might need a different debugger. I don't know if this is only compatible with our SAMD devices. I guess I should look it up. I'm gonna need to order a separate debugger. I'm gonna need to put that order in soon. Oh, thank you. That's not too bad. That's not too bad at all. Difference here. I guess it's isolation. It says ISO. In addition to the same functionalities as the ST-Link V2, the V2 ISOL features digital isolation between the PC and the target application board and withstands voltages of up to 1000 VRMS. That seems reasonable. Let's see. Oh, there we go. Spider, and then $8 to get the isolated version. Basically what that means is if something goes terribly, terribly wrong with your board, and somehow the debug pins end up like really strongly zapped by like 1,000 volts, then it won't destroy your computer. Honestly, pretty reasonable. I'd say it might be worth the extra money. Direct 78.72 versus 79.54. Gotcha. But I probably should get one of these. And probably the isolated version. Maybe I can just look for a SAMD microcontroller and then not have to worry about it, but of course that means redesigning all this microcontroller layout. Okay, so that being said, I should break out the debug interface. I'm going to need to make the connector for that. Well, I will need to make the connector. I will need to make the PCB footprint to put the connector on. Okay, let's... So I'll need to look up the layout of the ARM like debugging interface. So let's do that. A 2.54mm connector. Standard JTAG and serial debugging. Oh, you know what? I believe the document I was looking at had that pinout right there anyway. Let me go ahead and scroll down. There we go. Okay, so we are going to want a debugging connector. I feel like we should probably just break out the JTAG pin, put the JTAG connector in its own block. So look at What else we need? Okay, so we need in ATST. Might as well use the exact same pen names they're using so no one gets confused. Those two move around individually, actually. There we go. For a bit longer, let's make these. And then go. The bus connectors. 1, 2, 2, 3, 4, 5, 6. No, these should be facing the way. There we go. And we'll have a little, guess this is technically a bidirectional port. Data sheet somewhere. Install this. EB4. Oh, look at that. It's already labeled for us. That's wonderful. These so we don't have to remember the names. Okay. So. That there. So that's not even the right pen. Hold on. That there, actually. B, which is GPO. 15 is JTDI. Oh, and those are also labeled. I'm being extremely silly. Listen, you can't expect the streamer to be able to see anything. LGT. Because I spelled it wrong? Let me check the, Did I spell it wrong or did I spell it wrong? Okay, no, it is JTMS and they spell it wrong. Okay. Not my fault. Hashtag not my fault. JTMS. There we go. And switch that as well. JTMS. JTCK and JTDI. So wow, that is also on the wrong pin. I am sleepy today. Goodness. I reset in Kirsten. Huh. Supposed to go to NRST? Guess so. Is extremely necrodancer. I appreciate it. This should be connected to our reset. I believe that this is, I believe that this just goes to the reset input. Let me see if there's other guidelines around here. Yeah, that's what I was saying as well. This sounds extremely necrodancer. what their reference design does for the JTAG debugging. JTAG and trace. Okay, there we go. There's the NRST here, which is connected to. There we go. Okay, so this is how they actually implement their reset. Some sort of ESD protection diode. Might want to look into ESD protection as well. I don't think I've ever done specific ESD protection work, but it'll be good to learn. Huh. Okay, but in any case, so this is just left floating. And it's got a capacitor to ground. But here, this line's just floating. In here. See if it gets pulled up there. No, it's not. It's not pulled up anywhere. I guess it just has like an internal pull up. Let me see if I can verify that on the data sheet or the reference manual. Set and clock control.
I was standing alone when this feeling washed over me. Suddenly, you have brought me to a new place. I don't want to wait
Oh, you're at the door? Alright, one moment. I've gotta go, let Pancake in. One moment. Be right back. This is a good opportunity to take a stretch break as well, so I'll be back in like 5-10 minutes. See you soon.
I was beginning to think what I see is only a dream, and then you taught me how to breathe again. I don't want to wait for the future, and I just want to say I love you now, and everything that I needed to erase has already changed, guiding me to eventually cross your path one day. I'm changed in half way. I cannot deny this feeling. You were made for me. Can you be the one to say, please forget the past, please forget yesterday. Forget yesterday. Forget yesterday.
On most nights, I'm just wearing my pajamas, staying up too late, 'cause I'm watching Futurama, thinking where's my drama, My life's no melodrama, leave it off the screen, 'cause it's got no genre. Sometimes I call my mama, ring, yeah, she's always my armor. I want to fly away, far from my mistakes. My baggage has too much weight, hey, hey. So my bed is where I stay. Tell the clouds that I say hey. From my mistakes, my baggage has too much weight, ay, ay. So my bed is where all from my mistakes. My baggage has too much weight, so my bed is where I stay. Tell the clouds that I say hey.
Hello everyone. I'm back. I don't know how much longer I'm gonna keep stream going for. I am getting pretty hungry, chat. No, I'll have to think about it. Level 1 NRST pin causes an external reset. Okay. Okay, so there is an internal pull-up resistor. Okay, that's good to know. So we don't have to worry about pulling up the reset pin or anything like that. we go. Twice for our reset circuitry, so that button will let us manually reset it. JTAG debugger can reset it, and then by default that pull-up resistor, that internal pull-up resistor, will keep it non-reset. Keep these one away from the edges, actually. They're less visible now that we've made the line width thicker. That's nicer. Move these over here so I can put them in their own box. Okay, this is coming along pretty well. I'm gonna want to connect this to our connector eventually. That's some pretty good progress for today. quick read through of this, and then I think we'll end it for tonight after that. Component placements and partitioning are critical to good layout. Separating analog and digital sections is recommended so that noisy digital signals don't interfere with sensitive analog parts. Digital signals and their corresponding return paths must remain in the digital section of the board and must not interfere with analog signals. Use of a single solid ground plane common to analog and digital sections is recommended. The ground plane must have a very low impedance. Cuts into the ground plane must be minimized to avoid return current path diversion. The VSS, VSSA, VRF- MCU pins must be connected to the ground plane with the shortest distance possible, which reminds me, did I put the close property on? Let me check if I need to put close on the decoupling caps. There we go. Okay, it looks like those don't need to be marked as close. Capacitor very close to the ADC input pin is recommended. 47 picofarads is a good starting point. Sounds reasonable. Go ahead and do that. We should label these actually. We should label these twice, I think. We can have one here. And one, where we're connecting to the capacitors. I think we should be fine to not have these, like, visibly connected. Fill that in there. No, wait. Fill that in there. And we'll want to basically do the same thing. That's excluding the bus. Back over here. CC1 and CC2. These should be 47 picofarads and close. So let's do that. The ADC voltage source must be placed distally in CU, and the ADC input tracks must be kept as straight and as short as possible. They must have a ground plane. They must have a ground plane on an adjacent layer. Reference has direct impact on the accuracy of the results. Right. Connecting the VRF pin to a low offset, low drift, and low noise voltage source is recommended. Play in VRF plus VRF minus. Don't believe we did do that. Extend that out. This over here. Yeah, perfect. And we can extend this out this way a little bit. Microfarad X7R dielectric ceramic capacitor. Carrots. Carrot. The 10 nanofarad one must be 0402. And a good place to put tea. Probably fine. Although it will. So much extra space just for this these capacitor labels. We'll put this 0603, 0402. One is 1 microfarad. Separate boxes. Don't have a VRAF minus, so we don't have to worry about doing it for that. It's starting to come along quite nicely. It would suck if I had to solder on all these capacitors myself, but that's what the PCB assembly service is for. They have a machine for it. Kind of machine that doesn't get bored. Ah! That's not at all what I wanted you to do with that. There we go. Figure out how this would look fast. Like that. All of that. Ooh. The DSS power supply pair should also be decoupled with filtering capacitors. Oh, right, I already did that. Is that saying that those capacitors should be added between VDDA and VREF+? Well, that would make sense, because they have to be connected directly to a ground plane. Trying to square that with what this diagram says. Microfarad and 10 nanofarad. Well, I guess it can't hurt to have all for it. All right. I think that'll do it for this evening. As always, I hope that you enjoyed the stream. I know I certainly enjoyed doing it. Unfortunately, we didn't get all the way through the PCB design process tonight, but what are you gonna do? Microcontrollers can be complex, and their decoupling capacitor requirements doubly so. Next time, we will probably work on the button connections, but that shouldn't take too long. So once we're done with that, it's probably on the PCB layout. So this is just the schematic. It tells us what is electrically connected to what, right? The PCB layout tells us exactly what wires go where on the PCB. So yeah, I think that's going to be most of next time. So yeah. tomorrow I'll be on playing Sonic Rush. That's right, folks. We finished up all the Sonic Heroes last Sunday. So now I'm just gonna be out and playing Sonic Rush. So look forward to that at 1 p.m. Central Time tomorrow. Be doing more Minecraft on Tuesday, more Spark 3 on Thursday. Yeah, if you enjoyed the stream and haven't already, don't forget to drop a follow so you can get notified next time I go live. If you want to check out previous VODs in this series, my VOD channel is linked in the stream description. We have a Discord if you want to ask questions out of stream, make suggestions about future Sonic games or future stream ideas, or if you just have suggestions for this hardware project, feel free to leave those there. You can also just use it to hang out and chat. !Discord in the chat to get that link. It should also be in my stream description. I have a Mastodon. You can follow me there if you are interested in getting more information on streams before they go live. Or just general musing sometimes. But yeah, as always, it's been lovely streaming. Hope y'all have enjoyed, and I will see you tomorrow. Of course, Pancake. See ya!